My name is Holly Mooneyham. I am a senior SRE at Cisco Meraki. I've been with Cisco Meraki since about 2015, and I look after a whole bunch of different stuff. But in particular, what I'm going to talk about today is involving a lot of our deployment infrastructure and how that's evolved over time. I do a lot of work in the cloud, both public, private, and sometimes literal. This was from a very particularly fun on-call shift on top of Mount Tam in the San Francisco Bay Area, and got to go work literally in the cloud for a little while. So just to define a couple of terms up front, we're going to be using these a bunch throughout this presentation, so I just want to get them out of the way. Immutable infrastructure is where you deploy some components, software, hardware, et cetera, and when things change, you replace them. You spin up a new set with the new code, and then you destroy the old ones, and you manage all of that churn and the burstiness and traffic shaping and various other things required to make that happen. Mutable infrastructure, on the other hand, is where you, again, deploy some components, but you update them when things change instead of replacing them entirely, and you manage the drift and desynchronization that can happen over time. So from there, let's talk about how not to build a better mousetrap. I'm going to talk a little bit about how we even got here in the first place, what it is we actually need, what our minimum viable product is, and then how we keep momentum on a long project like this that now is spanning multiple years. So, who are we? You might think from this slide that this is some corporate thing that somebody told me I had to put in this presentation, but no, it actually matters. Who we are and how we evolved to the point we're at now is a really important part of understanding where the constraints that we're working within come from, and where the organization's priorities are. Our engineers don't want to build the best back-end infrastructure in the world, unless they're on the SRE team, in which case they probably do. The rest of our engineers, though, want to focus on getting their applications out to production with as little friction as possible. And we want to make that as easy as possible for them. When I joined Meraki in 2015, we had a grand total of 98 engineers. We had 405 physical servers in, I believe at the time, 6 data centers. And Meraki was based around mutable infrastructure. 8 years later, in 2023, we have more than 10 times as many engineers, almost 15 times as many engineers now. We have more than 10 times the compute spread across both physical servers and various public clouds. But we're still based around immutable infrastructure. Why? Wouldn't immutable infrastructure be better when you have 5,000 compute instances you have to worry about? There's a couple of reasons we haven't done it yet. Social change is hard. People really like their workflows, and making big changes requires building a lot of consensus. We can't change the past. There were some very pragmatic decisions that were made that bought us a lot of runway to get here, and technical debt's expensive. There are multiple kinds of technical debt. There's mortgage technical debt, where you're making a big investment in an architecture that you know will give you a lot of runway, but eventually you're going to have to pay that down over time, versus credit card technical debt, where you build something in the short term that maybe needs a lot of active maintenance to keep it running. In this case, our use of mutable infrastructure is a mortgage. It's a decision we made to buy us many, many years of growth, and now we're having to reevaluate it. And change takes time. There's a lot of competing priorities, even within the SRE team, with various compliance programs and other things that need to get done. And we can't stop all non-SRE work for multiple years while we make this transition happen. We want things to be great. We want to be able to move to immutable infrastructure, but it's a years-long process, and we have to be good at what we're doing now to be able to get there. And that takes us back to the subject of this talk, transitioning from push to pull and managing mutable infrastructure at scale. So how did we even get here in the first place? What led us here? So to do that, we're going to talk about this. This is a mousetrap. We got to do some very fun things with these in my Principles of Engineering class in high school that we'll talk about in a few minutes. But our original deployment system at the time that I joined was Capistrano. It was a command line tool. You ran cap deploy, and it pushed your code out to a whole bunch of servers, and when you have 98 engineers, it worked fine. This is our mousetrap, and it worked well enough. We had a couple of mice to catch, and they weren't particularly smart. At SREcon23 Americas, Lauren Hochstein from Netflix gave a talk about the adaptive universe model and the unceasing nature of change. And some of the major points that he talked about were that change is constant, both inside and outside your organization. Needs evolve over time, and more complexity is inevitable as you have to rise to meet those needs. And so what you end up with is this board game from 1963 that I'm sure many of you have seen before in some form or another called Mousetrap. This is still a mousetrap, but it's a much more elaborate and complex system designed around a bunch of constraints. And looking at Meraki's deployment infrastructure over the last 8 years, we've grown from Capistrano to, oh, well, the back end of Capistrano doesn't scale. Let's replace it with Ansible so that we can scale more. Okay, well, the Capistrano front end is now also a terrible developer experience because you have to be logged in and run commands on a server. All right, let's replace it with Jenkins. And then later on, let's replace it with GitLab because it turns out Jenkins also has problems. And this was a very reactive process. Each of these iterations iterated on some aspect of the system that was causing trouble or didn't scale with our needs. And as we did this, we accepted more and more constraints over time. And as a result, we had to build a more complex system that didn't deliver on the core developer experience we wanted. But each one of these iterations taught us something important. They're all iterations on a push model, improving on some aspect of it. And what we ended up with was a mousetrap car. This was the thing that we ended up building with mousetraps in that Principles of Engineering class. And we raced them, and whoever got the race done the fastest got the most points on the assignment. It's a lot of fun. But what we need for Meraki is not a mousetrap, it's a car. And keeping the mousetrap at the heart of it is holding us back. And so we have to think about what are the constraints that are keeping that mousetrap there. A question that I get very frequently when I talk about this is, what about existing systems? Aren't there off-the-shelf tools that do these things very well that we could just use? And our needs are unique. We noticed that a lot of the off-the-shelf tools have a ton of focus on Kubernetes and immutable infrastructure. And once you get into the realm of mutable infrastructure, their features either fall short or don't work at all. We had a lot of challenges integrating with some of our other technical debt-laden systems, especially our inventory tools. And we were looking for the perfect system. We wanted to find something that met all of our needs and all of our wants and did exactly all of those things. And that just doesn't exist. When we accept all these constraints without thinking about them, we tunnel vision ourselves into a system that we can't find. And so push systems, for me, are my mousetrap. They have benefits. There's very fine-grained control. We have natural prioritization, and developers can coordinate things by talking to each other and deciding what order to do things in. They also don't scale. Synchronous locking of all resources makes sense when you have a small handful of machines, but 5,000? There's no way you're going to be able to consistently get all 5,000 machines to align at the same time. Production state's unreproducible, which is a huge problem. If something goes wrong, we can't say, let's go back to where we were an hour ago, because we don't know where we were an hour ago. That state is entirely an emergent property of the deploy process. And we're very vulnerable to drift. If a machine is offline while a deploy happens, it could get left behind for a long, long time. And to really illustrate this, I pulled this quote last week from Slack talking about Postgres migrations. If SRE needs the lock for any reason, there's a very good chance you'll have to reschedule. And this is a procedure to migrate in production that already takes like 3 or 4 hours. Nobody really wants this. Speaking of things nobody really wants to stare at a whole bunch of text from Ansible telling them that there were failures on a bunch of random machines that they don't care about. Service owners don't care about this. That's not important to them. They don't want to know that some random machine that has nothing to do with what their service is having problems. And so this is another thing that drives our developers crazy. And as we iterated on this model over time, another concept from Lauren's talk really came up, which is this idea of a local perspective. I've been working on this problem now for roughly 8 years, and it's really easy to get those constraints in your head and not think about them. It's really easy to get tunnel vision and just keep iterating on the thing that is the most painful or creating the most noise. But it's possible that what we need isn't a push model at all, and we really need to find out. And to do that, we're going to dive a little bit into what it is that we actually need. We're going to step outside of that local perspective and reevaluate the constraints that we've accepted due to tunnel vision. And the tool that I'm going to use to do that is something that I call Breaking Change Budget. Breaking Change Budget is a resource that we have to make social change easier. Like I said, social change is hard. People like their workflows. And this is a way that we can sell changes to them and have them be able to work with us. So Breaking Change Budget is something you earn by addressing pain, fixing that credit card technical debt that has really high interest, providing net new features that just weren't possible before, and building trust with your engineers. And you can take that breaking change budget and spend it on things like social change, breaking people's workflows, or removing constraints that are causing you problems and preventing you from building the system that you want to in the first place. And we decided for this project that we were going to spend a whole bunch of breaking change budget getting rid of the mousetrap, breaking away from the push model, and switching over to a pull, or as I call it, eventually consistent model instead. So how do we figure out what our breaking change budget is? Well, to do that, we need to go talk to people. And as it turns out, user experience teams are really, really good at this. User experience teams spend a massive amount of time going out and talking to customers, figuring out what their needs are, and then bringing them back to us. So can we take their techniques and use them ourselves? Absolutely. So for this, we designed a series of interviews with people within engineering, who are our customers in this case, to figure out a lot of these things. We wanted to discover what our users' needs were. We wanted to map out those constraints that actually exist. We want to understand what's painful about the current system and what will earn breaking change budget by fixing. And we want to make their voices feel heard to build trust. So what's the actual problem? This is a very important thing to consider as you start to look at talking to people. George Bentic, our PM on our camera product, loves to tell this story about customers coming and saying, George, we need a PTZ camera. And he asks why? What is it that you need a PTZ for? And they say, well, we have all these PTZ cameras, and we want to replace them with Meraki, but you don't have a PTZ. Now, we could go and build a PTZ camera, but those have a lot of problems. They have moving parts which break. They only record what they're pointed at. And that's not actually what the customers need. What they need is to cover a larger area with less cameras. And so instead of building a PTZ, what we did was we built a fisheye camera that has a 360-degree view of the room and records everything all the time. And then you can pan around it in software afterwards. It solves the problem better than what the customer was asking for to begin with. And I'll give you a more SRE-focused example involving compliance. During a recent PCI assessment that I was more involved in than I want to admit, I got the ask that we need to scan containers during or before deployment. This is what I'm going to call a prescriptive need. It describes a solution to a problem, but not what the problem itself is. The person who's telling us this need has already decided on a solution and phrased the problem in a way that leaves no other option except the one that they've already chosen. What we want to do is take this and turn it into a descriptive need, something that just describes the problem, which is we need to prevent introducing new vulnerabilities. This is still coming from the same compliance requirement, but it gives us a lot more flexibility to solve this in a way that makes sense for us, and there are many possible solutions here. Compliance is a place where you run into this problem very frequently, but requests for more resources are another great example. Someone might come to you and say, we need 600 gigabytes of RAM on some machine to run our service. And that's probably not what they actually need. There's probably something more going on there, and we need to drill into it to understand why and what it is that they really need and what the ask is coming from. So in these interviews, we decided to ask 4 questions about people's current experiences, 2 positive and 2 negative. We asked 2 questions about their requirements to discover what those descriptive needs are. We asked 2 implementation questions to help inform our tooling choices, because we have to make those very, very early, and 1 open-ended question to make sure that our users' voices are being heard. With these interviews, we interviewed both a mix of individual contributors and managers for 25 minutes per team, and we interviewed 5 teams that were as different as possible from each other. And sometimes when you do these, you just get straight-up conflicting answers. An actual quote from one of these interviews was, "I dislike magic," and another one was, "I don't want to think about the deploy system." So you have people who think, I don't want it to do things for me, I need to know what it's doing, and you also have people who say, I don't want to think about it, I just want it to happen. And these are places where we probably need to provide flexibility. This is still useful feedback, even if it is conflicting. So what did we learn from these interviews? Well, we learned that there were a couple of features that were very important. Rollout strategies and feature flags are big ones that I'll talk about in detail a little bit later, because we had to iterate on them a few times. And they are places where, by providing these features, we earn breaking change budget. In terms of pain, people had problems with reproducibility, speed, synchronicity, and documentation. Again, places where we can earn breaking change budget by fixing. But there were also some constraints that we have to navigate now. Time zones exist, technology choices are not entirely within our control, and there are exceptional cases that are just weird, and we need to be able to accommodate them. The synchronicity one is also interesting because it's a prescriptive need, but it's an inverse prescriptive need. People don't want the global deploy lock to exist in the first place. And honestly, it's kind of a design smell that indicates there are bigger problems. The descriptive need that's hiding behind it is they need to clash with only the set of things that actually affect them, and not SRE doing some maintenance on a completely unrelated system. So taking these learnings, we can start to figure out what our breaking change budget is and where we're getting it from. Now, it is worth noting that sometimes there are just unavoidable constraints. We want to keep this list as short as we possibly can, and even when there are unavoidable constraints, like compliance programs, we still get to respond to them on our own terms and figure out how to implement them in the way that makes sense for us. Again, translating things into descriptive needs makes this a lot easier. And sometimes we have to spend breaking change budget on these things, and it's not ideal, but sometimes we have to do that, and that's okay. So, what about guideposts? We know what our users need, but what do we want? We decided to look to the DevOps Research and Assessment Report's elite status to help us inform this, and it lays out a couple of guidelines for what you should be doing. Your deploy frequency should be on demand multiple times a day with a lead time of less than an hour. If you have an outage, you should be able to restore service again within an hour, and generally you want a failure rate under 15%. And these aren't terribly difficult metrics to meet, but they are important things for us to consider and track both in the current system and the new ones so that we know how we're doing. So let's go ahead and put all this together. We have all the pieces that we need to make our plan. We have breaking change budget, we have the things that we learned for our interviews, we have our unavoidable constraints, and we have our guideposts. And this is exciting, because now we get to decide what we want to take a firm stance on and make our design decisions. We want to decide where we're going to provide flexibility and where we're not. And so we decided to make this set of decisions very early. We're going to go with a model that is based on eventual consistency, declarative state. So any machine knows what the state should be at any given time, and we decided on what our core tool chains were. None of these principles violate any of the declarative needs that our customers expressed during our interviews. None of them violate our unavoidable constraints. And we decided to spend breaking change budget to remove other constraints which clash with these values. The eventual consistency, or the pull model change, in and of itself was very expensive because it breaks fundamental assumptions that people have about how the deploy system works and the level of control that they have over it. And once again, we're back to transitioning from push to pull. This is the earliest diagram that I could find in my Lucidchart scratchpad of what this system looks like. It's very basic, and that was the point. It just illustrates our main design principles. There's two software components here and how people and they interact with each other. This was all we needed to really get moving and evolve from it. We also decided in places that we really wanted to make sure we were providing flexibility up front. These were what people do with the system. We don't want to tell people what the system can do. We want to give them the flexibility to use it as a platform. We don't want to tell people that there are a limited set of ways to interact with the system. We want to give them the flexibility to create their own interfaces to it. And we have to support the unpaved road. Our goal was that we want to pave 80% of the roads that we want to pave the road that handles 80% of our traffic. We want to make this as low friction as possible and make it really well supported and robust for most of our users. But we need to make sure there is a road for the other 20%. We don't want to get to a point where those 20% of people just can't use our system because we're not flexible enough. And so this takes us to a concept called minimum viable product. Now, I love this concept because when you hear it, you immediately think the wrong thing. People hear about minimum viable product and they're like, yes, it's what you can get away with building given your constraints and not over-engineering it. And it's sort of correct, but for the wrong reasons. Minimum viable product is a process. It's about identifying what your riskiest assumption is and then designing the smallest experiment required to test it. You do that. If your assumption was wrong, then you adjust. And then you move on to your next riskiest assumption. It's not about cutting corners or trying to get away with building something that's inferior. It's about minimizing the amount of investment that you need to get rid of risks. You want to make the smallest investment of your time to build the smallest thing you need in order to know that what you're building isn't going to have problems. And we're going to go through a bunch of these throughout the rest of the process here. So we ran our process looking something like this. We supported one use case in our early experiments. It was a service that we ran and maintained ourselves, and it was something that we handpicked because we knew it was simple. We maintained it so we didn't have to interface with anybody, and we could play around with it and figure things out. For alpha, we wanted to target 10% of the use cases. The customers that we knew had services that worked well with our model and weren't going to create a bunch of friction. Beta, we wanted to open things up to more people, let people come in themselves and find the problems. And then for GA, again, we want to make sure we support 80% of those roads well and make sure there is a road for the other 20%. And at each one of these stages, we tested a bunch of assumptions. Early experiments. Can we even put code on a machine from inside a container that's running on that machine? Do our core toolchains interact with each other literally at all? What's the minimum scope of interface that we need to provide to people, and does our design give our own security team nightmares? And this stage ended when we got our first service that we maintained on the system. During the alpha, do people understand what it is we're building? Do our dependent services scale to running this system? Do our customers agree with the levels of visibility and flexibility we're providing to them? And for this stage, we ended it once we had 3 or 4 handpicked services using the system successfully. And for beta, is there enough documentation for people to self-service, and have we missed anything? Letting people come in that we don't pick is going to introduce places where there's just things we haven't thought about, and this is our chance to catch them. And this stage really ends with users who don't have those exceptional use cases are able to onboard onto the system without our help. So let's go ahead and build us a system. And to do that, we're going to start with our early experiments. However, I do need to make one important clarification here because I have an unfortunate naming collision. We have an internal tool at Meraki called Athena, which is a metadata storage system that we use for tracking version data. There is also an AWS service called Athena that has absolutely nothing to do with it. And this confuses the heck out of people. We really ought to rename it, but it is an unfortunate naming collision. So for the purposes of this talk, if I talk about Athena, I'm referring to Meraki's version metadata tool and not the AWS service. So with that, let's move on to the first component of the system, which is something we call the deploy agent. We run one of these on every host in our infrastructure, so that's roughly 5,000. And each one of them operates autonomously, meaning we have 5,000 copies of this thing running totally independently of each other in a big distributed system. Its job is to ask Athena what the intended state is, make it so, pulling artifacts wherever it needs to, and then report what that state is so that we can aggregate that data later. V0 of this, the very first version we wrote, was 15 lines of Ruby code. Was it scalable? Was it going to ship to the fleet? Absolutely not. But it was enough to start testing that first assumption of, can we get code on the machine from inside a container? V1, which has all the features that you see on this diagram, was about 114 lines of code. We've iterated a whole lot since then, and there's a lot more code now, but those 114 lines really validated a lot of our basic assumptions about the role of the agent and where it interacts with other components of the system. The second component of the system is called the deploy supervisor. Its job is to read that intended state from Athena, just like the agent, and then also read all of the current state data out of Elasticsearch, which is what we were using to transport all this data around, and then report on it to places like Slack and Grafana. V0 of the deploy supervisor was more lines of code. I lost sight of the MVP a little bit while I was building this, and that's okay. No project goes perfectly. I certainly could have built it more quickly initially just to test assumptions, but things worked out in the end anyway. And this takes us to our first big refactor, where we plug those two things into each other and do a little bit of sustainability, hygiene, and future-proofing. This is, again, now towards the end of our early experiments where we're thinking about bringing other people into the system, and we want to make sure that we're ready to respond quickly when we discover things that we need to deal with. And we're very, very far from done. This is a very simple version of the system that only does a couple of things, and that's okay. That's all it needs to do. And so from here, I'm actually going to go ahead and jump into a demo. This is going to be edited for various reasons, but this is essentially the system as it existed at the time that we started the alpha. We've iterated a bunch since then, but this is what we were showing people at the time. And to do it, I'm going to use the help of my good friend, the ZFS Goose. We had a problem in our firmware build environment where ZFS would just crash sometimes, and fsync would hang forever until you rebooted the machine. And so somebody drew this goose to post in wall every time we had to reboot the server to let everybody know. And we'll be using this as part of our demo. We'll also be using that service that we used, the actual service, for our early experiments. It is a Bastion host that we run for another engineering team. It's a container process that they SSH into and can then connect to other things within our infrastructure from. And so we will see if the pre-recorded demo curse gets me. There we go. So we're going to start in the code repo that actually powers this whole thing. I have made a commit here that adds our good friend, the ZFS Goose, to the message of the day when you log into the container. And we're going to go ahead and push this change up to our GitLab repo that hosts this and create a merge request for it. So now when we jump over to GitLab, we can see that we've created our merge request, and the pipeline is going to start running for it. This pipeline builds the container image, runs some tests on it, and then waits for us to do anything further. Now, I don't think anybody here wants to sit around for 5 minutes of the Elasticsearch gem installing, so through the magic of editing, we're going to jump ahead a little bit to when the pipeline finishes. It does take a frustratingly long time, but here we are now at the end. So with the artifacts built, before we deploy them, we're going to jump on over to Grafana. And looking at Grafana for our service, we see that we are currently at 100% of our machines running the version of the service that we expect them to, all 7 of 7. And at the bottom, we can see that the development instance is running a different version, and that's expected because we run a newer version of the service in development before we roll it out everywhere else. And so we're at 100%, everything's happy, and we can go ahead and kick off our pipeline. So in just a moment, we'll jump back over to GitLab and start the push process. This is going to push the container up to the Artifactory cluster so it can be distributed, and then do that right to Athena. Once we publish this new version to Athena for the development environment, the deploy agent running on the development instance of this service is going to see that the Athena metadata no longer matches what's actually running on the machine, and it's going to make it so. It does this without being prompted directly by any process, and it just does it when it has time and when it's ready. We also see that the deploy supervisor has noticed that the deploy is running and has posted a Slack message indicating that it is. And if we go ahead and jump on over to our Grafana instance and hit refresh, we can see that there's a new deploy in our list of deployments. It's currently 85.7% of the way done because, as it turns out, only 1 of our machines out of the 7 has changed, and so the other 6 are perfectly happy running the same version they were already going to. And so we've got 1 host pending now. And once again, through the magic of editing, we're going to skip through waiting for the container to pull and start running, and jump on over to when the deploy finishes. This is the supervisor noticing that the agent has submitted a report indicating that the new version is running, and that all 7 machines are once again running the correct version. And if we jump on over to Grafana and hit refresh one more time, we can see that things are updated, and we now report once again that 100% of our machines are running the correct version. And finally, when we jump all the way back over to the real service, we can see our lovely ZFS Goose that now shows up to everyone when they log into the development instance. And rolling this to production would be very straightforward. We'd follow exactly the same process. We would just merge the merge request first. So we'll go ahead and move on from there and take us to the alpha. This was where we started bringing in external teams. We picked a couple of people who had compelling use cases that fit what we were trying to do and were the lowest complexity cases. We showed them that demo that I just showed you, just minus the redactions, and gave them the documentation we've written so far and said, hey, go ahead and start trying to onboard yourselves, and wherever you hit friction, let's start working through it. And before we get into that, let's start with some famous last words from me. FYI, we're firing up the new deploy system, and it's about to put a bunch of load on Athena, I say to the team that maintains that service, promptly before their traffic graph does this. As it turns out, the deploy agent was several orders of magnitude more load than they had ever experienced on this service before, and our assumption about our dependent services being able to scale was not correct. The auto-scaling group on this thing, to its credit, was doing a really good job of trying. That said, it was just constantly churning up and down, trying to anticipate the load spikes. And so we spent a bunch of time here tuning the auto-scaling parameters of Athena, as well as adding some additional load smoothing to our distributed system to make it less bursty. And I'm really glad that we caught this and figured it out before we had real customers, and so we didn't really disrupt anybody except the poor owners of Athena. This was another thing that we had to iterate on a whole bunch during the alpha, targeted deployments. This was the #1 descriptive need that people brought up during our interviews. It had 3 different competing use cases. We had to rewrite it 4 times, and it now has the most tests of any part of the system because it's complicated. It was really hard to get right. This was a feature where we had to provide a lot of flexibility and extensibility. If you look at this diagram here, we have varying scopes of our infrastructure. We have we have the environment, we have clusters, regions, instances, all the way down to individual hosts. And people want to be able to flexibly target different parts of this. Version 1 of this feature was just host name level version overrides. For this host, run this other version. And all we wanted to know with this is, are we even on the right track? Do people think this makes sense? Very quickly, we iterated to version 2, where we also gave them cluster overrides, and we made adding future types a lot easier so that we could do it quickly once we knew what people's needs were. Version 3 was implementing strong data types and a extensible algorithm that allowed people to implement their own path traversal logic for figuring out what subset of our infrastructure something should touch. Will giving people the ability to write their own system for this be utilized, and will it address their needs? And then finally, in V4, we had to switch to an explicit key hierarchy instead of computing one on the fly, because as it turns out, those 3 competing use cases all wanted it to resolve in different directions, and we had to specify which one won. And this feature, people like it now. I think it's in a good place, but we had to iterate on it a bunch of times, and that's fine. So talking a little bit about paved versus unpaved roads, we wanted to know during the alpha, is the level of flexibility we're providing correct? And our conclusion was, we wanted to provide an API for make a deployment of your service happen, and then pre-write a whole bunch of implementations that cover those 80% of use cases for common patterns. If you fit one of those patterns, great. You can just use the one we've written ahead of time. If you need to do something slightly different, you can extend it. Or if you need to do something completely different, you can just write your own. And it ended up looking something like this. This was a quote-unquote API for writing code that would be run by the system. It's 5 methods and 1 constant, and that's really all it is. In reality, many of our deploy scripts only implement some of these. There's one that it's an extension of one of ours, and it just implements a slightly different converge method, and that's it. Converge being a method that says, hey, give you a version, and then make a bunch of stuff happen to make your software be running that version. And this took us up to our beta. This is where we started bringing in new customers outside of the teams that we had handpicked, and we're here to test more assumptions. Not a whole ton of core architectural change happened here, thankfully. So we're just going to focus mostly on where we found out our assumptions were wrong, and we had to iterate some things. A big one was avoiding complexity creep. A frequent point of debate with the system, and something we kept coming back to, was what functionality needs to be part of the system itself, and what are we going to leave outside the boundaries? What are we going to let people implement themselves? And ultimately, we kind of go back to the 80-20 rule. Is this something that we think 80% of our users will need, or is it something only that 20% will need? And without doing full UX interviews, this can be really hard to figure out. So we have to sometimes make some educated guesses or judgment calls and react if we find out we're wrong. So let's talk again about that path traversal feature. We got to a point where we could let people target subsets of the fleet, but nobody wants to. Nobody wants to write a bunch of logic that micromanages these entries in Athena to make the right parts of the fleet do what they want. And so we decided, okay, enough people need this that we're going to make it easier by writing something we call the deploy orchestrator. It's going to know how your service should be deployed and then do all that micromanagement for you so you don't have to think about it. We also made an assumption early on that people were going to be willing to do the work to write all of this logic themselves, and it was wrong, and so this was our response to it. This is a feature that we unfortunately haven't had time to build yet, but it is on our list to finish before we finish off the beta. We also discovered some blessings in disguise during the beta. Interrupts and changing priorities are unfortunately a normal part of every project, but we managed to make them work for us. During the course of doing this project, we all actually had to just press pause on it and not do any work on it for about a month? No, it was a full quarter. We had to spend a whole quarter not working on the project because we had to go do urgent compliance work. It happens. But we used that as an opportunity to demonstrate that the system was stable and that people could continue to use it if they'd already onboarded, and one or two teams even onboarded while we were doing our compliance projects, and things kept running relatively well without us really having to do anything. And that built a lot of trust that the system was stable. So to GA and beyond. I don't have a ton of things to talk about here because we're not here yet. We're still in the beta, we're still working to this point, but as we move into the GA, I'm starting to think about how we can use this system to do things we couldn't before. And one of those is host owner versus service owner. I talked really early on about how nobody wants to just stare at individual host failures and Ansible output. And this is sort of the next step of that, where we want to start sending alerts to the people who own the machines rather than the services. But this is a thing that probably is going to require a bunch of breaking change budget, because there's a group of people who are going to start receiving a bunch of alerts that they weren't before and probably aren't going to be terribly happy about it. So we have to generate some breaking change budget to do this, and a way that we're thinking about doing that is by building something called the deploy verifier. It looks at our APM frameworks, the external looking glasses, to see how our environment is running for real, and then if things suddenly go sideways, get us back to a sane state again. This is a thing we were never able to do before because of the push model requiring an operator. So we're really excited that we can try stuff like this. And this finally takes us to the full diagram of all of the different system components. We call this internally the Exodia diagram because you have to take all 4 of the diagrams I showed you already and smush them together. And this is where we're going to be as we continue to iterate on the system going forward. And I'm 100% certain this is not the final version of this. It's going to change again, and things are going to evolve more. So wrapping up, we talked a bunch about how not to build a better mousetrap, figuring out how we got here and stepping outside of our local perspective, thinking about what it is that we actually need and then what the minimum viable product that gets us there is, and how we keep momentum on a long project. Building stuff is a lot of fun. I get really, really excited when people talk about spending less toil getting their code out to production. I don't want somebody to say, I spent my afternoon deploying these changes, or I spent my entire day running a Postgres migration. I hate that. And when people talk about that being less and less of a problem, it makes me really excited. Having the opportunity to build stuff that's tailored specifically to our own needs is awesome when we get to do it, and we should make the most of those opportunities. And to do that, I've got a couple of tools to help you with your next big project. Question your constraints. Step outside that local perspective, understand how you got here, and figure out if those constraints are still relevant and if you should accept them or move on. Learn your breaking change budget and spend it in places where your constraints stop you from building the things that you want or need to build. It's a really, really valuable resource that you have to think mindfully about where you're going to spend it. Interview your customers. UX teams are amazing at gathering information, and their skills can really help you understand what your customers, in this case, whether they be actual customers or other engineers, need, and to get to those descriptive needs that are hiding underneath what people tell you. And MVP as a process lets you test those riskiest assumptions and keep testing them continuously with the minimal amount of investment as you move forward. It also lets you show off your work really early and often, and that can help you build a lot of trust that you're on the right track. I'd like to go ahead and give some special thanks to my wife, Lexi, for doing my video editing and redactions, as well as the copious amounts of feedback she's given me on this. My principal engineer, Scott McCool, who's been a phenomenal advisor throughout this entire project, and my colleague, Michael Zhao, who helped immensely with building various parts of the system and has been a fantastic partner to work on this project with. So thank you all for listening. Use those tools and go build something really cool.